Good afternoon to session 4. So let us,
Then,
before we go into instruction level parallelism, let me just summarize on what I have taught you yesterday. This is, you heard about the word SMP, UMA, NUMA, you can call it as UMA, I don't know. UMA is a name in Indian name, girl's name. Okay, so I don't know anything else. Yeah, distributed memory and then shared memory. Okay, so we were talking about all this because going forward, our discussion is going to be on multi-core processor. Okay, so there will be multiple processors connected to memory. So there are some categories based on how these multiple processors are connected to the memory. So one simplest configuration is all multiple cores in a chip connected through a system bus connecting to a one physical memory. So again, remember when I say memory, it is the main memory, which is a RAM, and it doesn't talk about the cache memory inside the processors. Now, the simplest configuration, all the processors connected to a physical memory, and the physical memory is also located in one single location. It is not distributed over different places. So this configuration is a shared memory. The memory is shared, but it is not distributed shared memory because we have the memory in only one place. So you know the difference between what is distributed shared memory and a shared memory. And when we say that a memory is shared, that means there must be more than one processor core in the system. Otherwise, if only one processor is using the memory, it is not a shared memory. It is only for that processor. So we are talking about multi-core. That means two or more number of processors. And as you know that any processor to execute something, it needs a memory to store a code and data. And that memory could be located in one place, shared by multiple processors, or it could be distributed also. The memory also can be distributed. So when we talk about the simplest configuration, wherein one shared memory is there with multiple cores accessing it, is a shared memory system. And all the processors, when they are equidistant from the shared memory, that means all of them are connected through an interface which is more or less of same length reaching the physical memory. They all have a uniform access time. When I say uniform access time, the time taken for a processor to read from the memory or write into the memory, it doesn't matter whether it is a read access or write access, a processor needs to read it or write into a memory. So this accesses can be any type, it can be read or write, but all of them will see the same delay in terms of reaching the memory because the memory is located in one place. And one more thing, you might have heard about random access memory because we call RAM a RAM because any location in the memory is equidistant. You know, access time is not specific to a particular location in the memory. So based on the distance, as well as because we are talking about a main memory which is mostly built with random access memory, DRAM, the access to any bytes in the memory will have the same access time, and all the processors also will uniformly having a same access time. This is called a uniform memory access structure. So uniform memory access is possible in a shared memory. It is not possible in a distributed shared memory. When you say non-uniform memory access, indirectly it means that it is a distributed memory and different processors are having different access times. It is not uniform. It is non-uniform access time. So when we talk about these two, we are actually referring to the memory and the access time between the memory and the processors. If it is uniform between the processors, it is called UMA, otherwise NUMA. So you can make out from this that A distributed memory cannot be a uniform memory access. It has to be non-uniform memory access because memory is distributed over different locations and different processors will have different access time. Now, let me talk about distributed shared memory. In that case, we will not have only one location. We may have memories attached to each processor also, which are called local memory. Then this processor will have less access time compared to memory which is connected to another processor. So the memory is now distributed over different locations. It may be attached to a processor or it may be connected to a different network. It may be all around the place. So it is a non-uniform memory and distributed. So we spoke about memory. Now what is SMP? SMP talks about processors. It doesn't talk about memories. It is talking about processors. And SMP is a multi-core processor where they are all symmetric multiprocessor. When they are called symmetric, only when the multi-core processors are of same type, almost same type. That is, if you are having ARM 7 TDMI, one particular version of ARM, you will have the same version of ARM in the system. Or if you are using Intel iCore 7, all of them are Intel iCore 7. So they are similar processors and they have equal access time. That means they are configured in the UMA configuration. So SMP processors are using the UMA configuration for connecting to the memory. That means there is only one physical memory and this SMP processors, then we call this as a SMP processor. So I hope it is very clear what is SMP, what is UMA and what is NUMA. Okay, NUMA. Now let me just open up the question for the topic what we covered yesterday. Please go through this and take a piece of paper and write down the configuration for each of them and see whether the option is correct or wrong. Only 21 people have responded. Can you be a little bit quick? Take your time. Newang, I didn't get what you are saying. Some more connection low. Can you explain what you mean by that? Okay, 47 out of 55. Shall we stop it? Or while it is going on, let me tell you, or I'll share the results. I think, let me give one more 10 seconds, I will give more. '49. Oh, can't see the poll. Uh, if you can't see the poll, maybe you disconnect yourself and connect again. I'm not sure what is happening. Log in again. Because many of them are okay. Okay, guys, let me end the poll because we are losing time. Let me share the results. What do you think is the right answer? Anyone?
C.
B for boy, D for dog.
C. Cat.
Cat. Okay. Anyone else? Don't go by the majority. Let me just look at it. Here, one instruction line is coming and the same thing is fed to this. So you are sure that it is, sorry, data. It is data. So it is SD. And instructions are two different lines are there. So MI. There are, first of all, okay, two are there. Fine. Now what is this? Here, this is the processing element. CPU is here. This is a control unit. IO, we don't care. This is the memory. So there is one connection to memory and there is another connection to memory. That's all. There is nothing else. There's only one single processor. Looking at single core itself, you have to be sure that it has to be SISD. All other configurations will have multiple cores. Only this, if there is a single core, it has to be SISD. Okay, this is SISD. That means C is not correct because it says SIMD. Okay, it may be correct, but look at this one. How many cores are there in this? Again, processing unit is only one. This is control unit and this is the memory. So this is also SISD. I never said that I will give you all four. I can repeat the same. So this is also SISD. And the last one you see here, instruction, there are two things coming. So even though this set of four are getting the same instruction, these four processes are getting different instructions. So it is MI. And data, anyway, everybody is getting separate. Okay. So MD. So there is nothing, no option is saying MISD, SISD, SISD, and MIMD. This is also wrong. This is also wrong. Everything is wrong. So this is the correct answer. So we have 13 people who have answered D. You can pat yourself. I cannot come and pat at your back. But these 13 people have done correctly. I hope the remaining people got it where they made a mistake. Okay. If you still have doubts, please get back to me offline. Okay. I am not going to touch upon a clean configuration after this. Okay. Now, let me see how many of you get it. Thank you, Mezumfu. I will not stop the recording, otherwise some things are lost. If some audio is heard, someone is. Can you? If somebody is hacking, Yanlin is hacking me. Zoom. Okay. So correct answer is visible there. Okay, I didn't explain about cluster in the morning today. Cluster is nothing but a distributed system with multiple independent computing systems connected through some network, and they have a distributed shared memory. So this is a good example of that. All these are all having individual its own OS and its own memory, and they're all connected. So similar to a distributed computing cluster of systems. Whereas these two, if you see, both of them have a single shared memory, and all of them are connected to it with the same system bus. So the uniform access is there. So both of them are SMP. So SMP cluster is the right answer. Okay. So let me go forward. I hope it is clear. Okay, because I did not record the discussion that we had for the last quiz, let me come back. So just I missed out explaining this. So this is a good example of SMP, and all the options are correct, and the correct option is E. Okay. Let us start with the ILP now. And I want all of you to read this book which all of you have. Appendix C talks in detail about ILP. Please start reading that book. After this course, anything that you need to learn in your life, maybe if you join some other master's course or PhD course is different, but you may have to learn on your own. So cultivate the habit of reading the book and understanding it. I am following this book very closely. So you can start reading this book. Appendix C, you can start reading from today. That's a homework actually for today, for the weekend. Okay, now let me talk about what are we spoke about functional parallel architectures. Based on the functionality, if we can parallelize some of those things, we call them as functional parallelism. Executing the instructions in parallel is one way of achieving the parallelism. Running threads are in parallel is one, and then maybe having a multiple processors with a distributed memory is one. So in this category, we are going to talk about pipeline processors, VLIW and superscalar. I will come to that after this topic. So our focus for next 3-4 classes will be this. Today is the most important thing. If you understand today's class, the rest of it will be easier to follow. So please pay attention. Do not sleep now. Okay. This is an example of unpipelined structure wherein instruction gets executed on different stages. Different operations are performed on the instruction, and then the next instruction is starting only after this is completed. So there is no overlap of execution in the instruction. So we are not exploiting any parallelism while executing the instruction, because we are completing one instruction and then only starting up with the next one. So it is not an ILP processor. Okay. So a non-pipeline processor, we see that instructions were executed one after the other without any overlap. The execution of instructions may involve the following activities or sub-steps, maybe more sub-steps, but these are the major steps. Instruction has to be fetched, then it has to be decoded, operands have to be fetched, instruction execution should happen, then results should be returned back. So these are the 5 steps in the same order should happen. Some processors may combine some of them, some may split an operation into multiple things. It is left to the implementation. But in a higher level, these are the 5 steps involved for executing an instruction. Okay. Now, what is ILP? It's a measure of how many of the instructions in a computer program. We have so many instructions in a program. How many of them are executed simultaneously by the CPU? So we may pick some set of them in the sequence and start executing them in parallel. So we don't finish one instruction and then only take the next. Then it is unpipelined or non-pipelined. But we take one instruction, before we complete the remaining steps, we take one more. Since CPU takes one more. So that is what is called a pipelined architecture, and that is what is called instruction level parallelism. So one thing I want to make it clear to you, ILP must not be confused with concurrency, which is achieved by running multiple processes with the help of OS. So we spoke about processes. We said that given a single CPU, OS takes care of scheduling different processes on the CPU, right? We said that it will run for a while, then context switch will happen, some other process will run, then another process is running. So that is also concurrency. Instruction execution is also concurrently executed. These two are different. When you talk about a process running in the CPU, it is only one process running. That one set of execution is running. And when another process is coming into the CPU, we are removing this and then bringing another process. So OS is doing the job of context switching between processes. They are not running actually in parallel. Only thing is we are getting an impression that they are running in parallel because we see that all the processes make progress. Because OS takes care of running them for a short duration and gives us a feeling that everything is happening at the same time. But in a uniprocessor system, when you say that OS is scheduling multiple processes, all the processes are not running simultaneously at the same time. Only one process is running. After some time, another process is running. Only thing is they are running so fast that CPU is given to all the processes in a much faster rate than we can conceive. We feel that all the processes are running in parallel. That's all. So that concurrency is different. This concurrency, what we talk about ILP is, we talk about processes enable parallel execution of sequence of instruction belonging to many sequence of execution in a single core. Okay, OS operating system support processes running on a CPU in parallel, but they do one at a time. If it is a multi-core, maybe multiple processes will be running in parallel. Okay, in a single core, only one process is running at the same time. So I am talking about process now. Now let us see. On a single core, OS gives an impression of all processes making a progress by time sharing the CPU. So though at any point in time, only one process is running. At any point in time, only one process is running. Whereas ILP is different. This is a hardware feature that exploits parallelism in the execution of instruction sequence. So ILP is working on a particular process. Suppose when the OS has scheduled a process and the process is running in the CPU, assume that it is a single core processor, one set of instructions belonging to the same process is running. We are trying to parallelize the execution of those instructions using ILP. So process level parallelism is little higher abstraction, whereas instruction level parallelism is at the instruction level. So it is happening within the process. So process can achieve doing more and more if this ILP is there, because multiple instructions are getting executed simultaneously. So in this case, what happens is, given a cycle, given a cycle, multiple instructions will be in different stages of execution. Different instructions are executed simultaneously at the same clock cycle. So it is quite different. It is nowhere linked to concurrency that we get in a process. This you should have a clarity. So that's a goal of this slide. So let me go into ILP now. Before that, let me talk about what is the parallelism that you see in ILP. If you look at this, each of them are one CPU cycle. Okay, assume that they are all RISC processor. We are talking about mostly RISC now. That means every instruction, most of the instructions are going to take only single cycle, because mostly you know that RISC processors have instructions such that all of them are single cycle instruction, the majority of them. So if you see this slide, this is actually showing you one instruction going through multiple stages of execution, getting completed, and next instruction starting. So there is no overlap and there is no pipelining. So it's an unpipelined processor. Okay, no parallelism. It is a serial or no parallelism. Now look at this picture. There is some overlap. This is one instruction. It is another instruction, but this is picked up maybe after 3 cycles, but it is running in parallel. That means during this cycle, both instructions are getting executed. In the sense, this instruction is in different stage and this is in another stage. Remember, when I say different stages means different operation, like fetch, decode, execute, memory, or write back. So this portion is executed by one piece of hardware, and of this instruction I, this is an instruction I plus 1, it is getting fetched here. So this hardware, which is taking care of fetching the instruction from the memory, is different from this hardware, which is maybe writing into data memory. Okay, so hardware which is handling them are different, but they happen at the same time. The fact that different hardware modules are handling it, one is fetching your instruction, other module can be writing into data memory. Suppose this is a data memory, this module is writing the result into data memory, or maybe accessing some operand or a value. This is the instruction memory. Okay, one module is fetching data from fetching the code from instruction memory. So this instruction is getting fetched here. That's another module doing the job, whereas another hardware module which is maybe writing into a data memory or reading from a data memory. So there are two different modules which are doing it. So it can happen in parallel. That's why it happens in parallel. When I say overlap, it is happening at the same time in the same clock cycle. This instruction also makes a progress. This instruction also makes a progress. Okay, this is the crux of ILP. Most important thing to understand. So this is overlap. It is true that it is overlap, but a new instruction is not entering the pipeline on every CPU cycle. Let me explain what I mean by every CPU cycle. This is one CPU cycle, an instruction has entered. Always remember, the first stage of a pipeline is an instruction fetch. Unless we fetch the instruction, we cannot do anything with that. So always the first stage will be fetching the instruction. Now, if you look at this picture, this instruction is fetched in this clock cycle, but next 2 clock cycles, there are no instruction fetched. And then one more instruction is fetched. So instruction is not coming in on every CPU cycle. In this case, it is not coming every CPU cycle. Let me look at this picture. This is one cycle is over here. One instruction has come in. Now the next cycle, another instruction is coming. Maybe if I have shown one more, I will show like this. That means I will fetch another instruction in the next cycle. That means I am fetching one instruction every clock cycle. So this is fully overlapped. It's not fully overlapped means it is not like this. That is different architecture. It cannot be overlapped 100%. It will be overlapped like this with one shift. If it is like this, when it is shifted by one clock cycle, that means you are getting one instruction entering the CPU every cycle. Okay, every cycle one instruction is getting fetched. Now let me clarify one more thing. One second. So why do we say that I cannot fetch another instruction in the same clock cycle? Because the hardware involved in fetching the instruction is only one module is there. It is now fetching one instruction here. So during the same clock cycle, I won't be in a position to fetch another instruction because I have only one module. So I have to have at least one clock cycle delay and then fetch the next instruction. That time what happens? The module which is fetching the instruction is free because it has fetched it and it has passed on the instruction to the next stage. So remember, when in a pipeline, an instruction is going through different stages, there are different modules managing it independently. So it is like a handing off job. One instruction is taken, fetched from memory and given to the next one. Then it is given to the next. It is going like this, getting propagated into the pipeline. Because this instruction has moved here, this module now can fetch the new instruction. Okay, so it has fetched instruction I here. Now it can fetch I plus 1. Similarly, here it can fetch I plus 2. That is the idea here. Okay, now I am showing you 5 stages here. Here 9 stages. It is called a deep pipeline. Anything which is taking more than 5-6 stages, it's a deep pipeline. The pipeline is very deep. That means what? An instruction entering here takes 9 cycles here to get completed. It has to come through this. One more thing, remember, when the instruction is getting into the pipeline, it cannot skip one and then save time and then jump over. Okay, it is like this. When you join the college, you have to finish 5 years before coming out of the college with a BE degree. You can't say that I will take a break for 2 years in between, but I want a degree at the 5 years, end of 5 years. It's not possible. You have to go through the 5 years to get the degree. So similarly, once the pipeline structure is fixed, they have to go through it. Instruction have to go through it. Whether they do any useful job in a particular cycle or not depends on the type of instruction. I will talk about it with example. Do not worry about it. But they have to spend time in each of the clock cycles before they see the world outside. They come out after completing the execution. So I am explaining it so well here so that the remaining topics or remaining part of this discussion today will be easier for you. Okay. So level of parallelism is different in each cases. How many cycles are getting overlapped is the level of parallelism. So, and depth is more, it takes more time for an instruction to come out. So let me ask a question now. How many cycles that an instruction in a 5-stage pipeline take to complete? You don't have to reply. I'm not going to start a poll. It is very obvious. It will take 5 cycles. Okay. It will take 5 cycles as I explained to you now. After initial 5 clock cycles have elapsed. Now, one more thing I am going to explain to you. Okay. Let me maybe explain this in the next slide. So hold on. Okay. This you will understand it next. Now, I will defer that discussion. Okay. Now, there are 5 stages. This is a RISC pipeline. Instruction fetch, decode, execute, memory access, and write back. Pipelining is an implementation technique whereby multiple instructions are overlapped in execution. I explained this just now, and it is not visible to the programmer. Each step is called a pipe stage or a pipe segment. Okay, this is a pipe segment, this is a pipe step or a segment. Each of them is a pipe segment. So how many stages are there in this? You may see that instruction is a PC, suppose program counter is pointing at some address 1000, that instruction is fetched here and it is decoded, executed, and during that time when the instruction moves here, one more instruction has to be fetched. But here picture is showing that it is update is happening and then only coming back. Don't think that update happens only at the end. The PC is getting updated automatically. This update is not a, it is not going to take one cycle for update. Okay, PC is updated irrespective of this particular sequence. Don't think that it is have to complete and then only it will be updated. If it is there, it is an unpipeline. So maybe I will do one thing. I will put a dotted line to say that it is not that instruction PC will be incremented only after this, because most of the books show like this. So I have written like that, but it is need not be misunderstood like that. Okay, so let me explain. Now one PC value is 1000. It is fetching the instruction at 1000, and then the instruction is moved here. The value which is in IR instruction register is moved. It is copied here, and then decoding happens here. During the time, in the next cycle, 1004, if you assume that instruction is taking 4 bytes, 1004 address will be fetched. Okay. So how many stages are there? There are 5 stages. Now, remember one thing, update PC is not done in the same sequence like this. It is done without using a different ALU, separate ALU. There is a separate hardware which takes care of updating the PC. Okay, so I showed you in the non-pipeline CPU design, even updating the PC was done through ALU. That is a very primitive design we saw. In a high-end processors, updating PC is done automatically with the separate hardware. It doesn't depend on the ALU which is used for execution. Normal ALU is used for instruction execution, not for updating the PC. This you should remember, make a note somewhere. PC updation happens on a separate hardware on every cycle, because you need to have a next PC address ready for fetching the next instruction. Remember, in the pipeline, I told you every cycle there is one new instruction coming in. So we have to have a new PC computed immediately within the same cycle. We should not use a ALU somewhere down the line. Okay, that is for instruction execution. Okay, so pipeline, it is called a one cycle that I say is a machine cycle or a CPU cycle. So that is the frequency with which the CPU is running. If you hear that CPU is running at 2.4 gigahertz, then your CPU cycle is 1 by 2.4. Okay, CPU cycle is nothing but this frequency. Now, some processors actually multiply this by 2, even multiply this by 4 to speed up the execution of processor. Okay, so you have to look at the specification of the processor to know whether the CPU's clock cycle is same as whatever is the clock frequency given. Most probably it will be same or maybe more, 2.4 gigahertz or something, maybe more. CPU may be running double the rate. Okay, you have to look at the specification. So that is a cycle or a machine cycle a CPU is running. That means every instruction is assumed to be taking one cycle in every stage. So every stage takes one CPU cycle or maybe more sometime, but let us assume that for most of the cases in a RISC processor, it will take only one cycle. So you can assume conveniently on every cycle the instruction moves, but there are some conditions wherein it cannot happen. We will talk about it. Okay, otherwise you can assume if everything is fine, ideal condition, the instruction move every cycle, they move into the different stages. Okay, now what is the latency? I'm defining some words here. Latency is a time taken for an instruction to come into the pipeline from the time it came into the pipeline till it exits the pipeline. Okay. How many cycles an instruction effectively takes from the time it came into the pipeline till it goes out of the pipeline? That means goes out means it gets executed fully. That is the latency an instruction sees, or it has to go through. If you look at from the instruction perspective, every instruction has to take 5 cycles in this case, in an ideal condition. It is like this. Each one of you in the college will take 5 years to complete the degree. So that you cannot avoid it. But if you look at any year, now right now in 2020, there are so many batches are in the college now. They are in different stages. Some batches in first year, some are in second year, third year, fourth year, and you are in final year now. So instructions can be considered as a people, students who are in the college. And if you entered in 2015, you are going to take latency of 5 years to come out of the college. So similarly, every instruction that enters the pipeline in this case is going to take 5 cycles. Okay, so its answer is 5 cycles. Assume every stage is taking 1 cycle. If suppose for some reason you take a break and then you spend 1 more year, then you may take more than 5 cycles, but on an average, you cannot come out of the college less than 5 years. Similarly, instruction also maximum it has to take 5 cycles, but it can take much more than that. Minimum it should take 5 cycles, but it can take more than that in case of some difficulty in completing the execution. Some stage there may be some difficulty that we will worry about it later. Now that is called latency. Now what is throughput? Throughput is of a pipeline. We are all talking about latency of the pipeline, latency that an instruction faces or experiences by going through the pipeline. Throughput is what is the throughput of a pipeline? It is the number of instructions that can leave the pipeline each cycle. So on an average, if I look at 1 hour of execution, what is the number of instructions that come out of the pipeline? Then that gives us a throughput of the pipeline. How many instructions it is able to execute it in a given time. So it cannot be more than 1 instruction per cycle, because we have only 1 pipeline. Every cycle, maximum 1 instruction can come. You cannot have 2 instructions coming out within a cycle. But if you find an average, it may be less than 1. But ideal case is 1 instruction per cycle. But if you look at the throughput for a longer time, you may see that it is only 0.8 or 0.7 instructions per cycle. But the best value is, maximum value that it can be is 1 instruction every cycle. It cannot be better than that. You cannot say that I will get 2 instructions out of it. As I told you, no instruction can just jump out of the stages. It has to follow all the stages and one after the other. Suppose 1 instruction has entered first, it has to come out first before the next instruction comes out. Order cannot change. Okay, order cannot change. It cannot skip a particular stage, and more number of instructions cannot come out from a single pipeline. Okay, I hope this is clear. Let us now look at some equation. Okay, very simple equation. Assume there are n instructions. They execute in n into k cycles in a non-pipeline processor. I am taking some random n instruction, and then I see that all of them are taking k cycles to execute. Then number of cycles taken for all the n instructions to get completed is n into k cycle. It is very clear. You cannot add them, you have to multiply them. Remember, it's an unpipelined CPU. That means 1 instruction takes k cycle, then next instruction is not overlapped. So that is also going to take k cycle. Then similarly, the nth instruction also will take k cycle. So the total cycle taken will be n into k. It's not n plus k. Okay. So I'm talking about a non-pipeline, which is a no overlap. There is no overlap in the execution of the instruction. So they all take k cycles each. Now I'm trying to find out, in this generic case, if I take an n instruction and a k cycle, similarly, let me assume I have a k stage pipeline. Okay, I am having a system which is taking some k cycles. So let me now what I do. In a non-pipeline case, it was taking k cycles. So I built a CPU which has got k stages. I somehow divide it into k stages, and then I am going to pass one instruction after the other. Every cycle I am going to pass an instruction into the CPU, into the pipeline. Now I want to see how many cycles that n instruction would take if it has to go through the k stages. So by now you can start thinking about it. Let me explain. Let us just, without going into any of this, whatever is there, let us try to get the answer without even looking at it. Now I am saying that it is going to be k stages. That means what? If I give one instruction here and I fetch from instruction memory and then it comes here, it is going to take k cycles before that one instruction, I instruction. Okay, let me talk always about I as some instruction I, and assume that there are no instruction before. There is, the pipeline is empty. Pipeline is empty. There is no instruction in the pipeline. I am fetching the first instruction, which is I, okay, from the memory. Now all the stages are empty. Instruction I is coming into the stages, CPU cycle. So on one cycle, it will be passing this stage and then coming into this stage. So I will be here in the next cycle. Now, when the instruction I has moved, suppose this is the first cycle, this is the second cycle. In the first cycle, I was here. In the second cycle, I would have moved to this stage. Now I plus 1 would have been fetched and it will be here. Similarly, third cycle, now let me write it in a different color. I would have moved here. It is doing some processing. Don't worry about what it is doing. I plus 1 instruction would have moved here. I plus 2 will be now fetched and it will be here. So you can imagine this is what it is happening. Now imagine the situation where after k cycle, what happens? I comes out. I gets completed. So now for instruction I, how many cycles it has taken? How many cycles it has taken? 1 second. Okay. Correct. Okay. Very good. I got some answer also. Ekamin has given the answer and she is correct. Okay. So this instruction takes k cycles. So you can say that first instruction k, as a small k it is, it takes k cycles. Now look at I plus 1. When I is coming out, I plus 1 is here. I plus 1 is here. I plus 2 is here, and so on. Now imagine after the k cycle, what will come out at k plus 1? The instruction I plus 1 will come, because it is just waiting outside. It will come out. At k plus 2, sorry, my handwriting is so bad because I am trying to write it through mouse. K plus 2 will, at the k plus 2 cycle, I plus 2 will come out. So we are taking n cycles, okay? N instructions we are taking, which is much more than k stages in the pipeline. So n instructions we are considering, and then k stages are there in the pipeline. We are seeing every instruction is going to take how many cycles. We saw that the first instruction took k cycles because the pipeline was empty, and I said that instruction I was the first instruction to enter the pipeline, so it has to take k cycles. But the remaining n minus 1 instructions will not take same amount of cycle. It will only take, each of them will take one cycle each. Very good. Sunanda also came up with the answer now. So the remaining instructions are not going to take the same k cycle because they are all coming in parallel and executing. So each of them are going to take only one cycle. So effectively, the total number of cycles taken is k plus n minus 1. Okay, you can put a bracket, doesn't matter, but still to say that the first instruction takes full k cycle, whereas all the remaining n minus 1 instructions take one cycle each. So you have to only count n minus 1. So k plus n minus 1 cycles is the number of cycles taken in a pipeline structure with a k pipeline, k stages. That is important. Okay. So this is what we derive. Okay. I hope this is clear. Now you know that n into k is much higher than k plus n minus n plus 1. Okay. Sorry, I made a mistake here. Okay, copy mistake. So I will change it. Okay, this is n minus 1. Okay, I hope this is this correction I will have to do, and then one more. Okay. So let me explain now the same thing. Instruction I is, while here, when it moves to instruction decode, I plus 1 will be here. So this is the first cycle, this is the second cycle. And then I plus 2 instruction, by the time it comes, get fetched, this will move to ID and instruction decode, and this instruction would have moved to EX. So this is very intuitive how things move. These are the different stages. So if you see, these are all actually different stages of the pipeline which are not occupied by any instruction. Okay, it is only IF is occupying it because no other instruction is in the ID stage. But here, if you see in this cycle, 2 instructions are there in the pipeline in total. One is in ID stage and one is IF stage. If you see the third cycle, the instruction is filled with instructions. 3 instructions have come in, so they are all in different stages. So if you see that the maximum overlap will happen in the 5th cycle, which is the 5-stage pipeline. On 5th cycle, the pipeline is full now, so different instructions are in different stages. So that is why we are getting a parallelism now, because while one instruction is getting executed, other things are making a progress. They are not waiting. In a non-pipeline processor, every instruction has to wait before the previous instruction is fully executed. Whereas in a pipeline instruction, the instructions are not waiting. They are one behind the other, but they are controlled by the completion of the previous instruction. They cannot jump out and then come early. You are in the queue. You cannot jump out of the queue, but you are entering the queue at least. So you are making a progress as the instructions, as the time progresses. Time is like this, clock cycles are given and instructions are moving like this. Okay. So if you understand this clearly, different stages, and then now you see here, let me explain how one instruction is coming out. In instruction 5, clock cycle 5, this instruction I is in write back stage. So at 6, I has come out, I is completed. At 7, I plus 1 is completed because it is completing the write back now, the last stage. So it will completed now. At clock 8, I plus 2 is completed. So this I took 5 cycles, okay, whereas all of them are seen. If you stand here, if you stand at the output of the pipeline and then see that who is coming out, you will see that I has taken 5 k cycles or whatever this number of stages. Then all remaining instruction you will see that they are completing in one cycle. So that is how you will see when you are standing here and then checking that instructions coming out. So effectively we are getting the benefit of pipeline here. Okay, I am sure you might have understood everything now, all of you. So one thing is n is much more than k in our case, then we can actually simplify this equation. Okay, so let us see that. So under ideal condition, only the first instruction takes 5 cycles or k cycles, and after the pipeline gets filled fully, all the remaining instructions take only 1 cycle each, and that is 1 instruction coming out of the pipeline every cycle. So that's the summary of this slide. Okay, now let me define some latency, throughput, and speed up for a k stage pipeline. Okay, I define these things now, and then I will explain to you what is latency, throughput. We defined it just now. Latency is what? How many cycles an instruction has to be in the pipeline. I said that if a pipeline is of k stages, then any instruction coming in needs to spend how many cycles? It will be k cycle. So latency of a k stage pipeline of an instruction will be k cycles, small k. What is a throughput? Throughput is number of instructions come out of the pipeline every cycle. How many instructions come out? So in an ideal condition, 1 instruction is coming out every cycle. So throughput is 1. Now what is speed up? Speed up is you have to compare how many cycles a non-pipelined CPU would have taken to execute any instruction versus a pipelined CPU. Okay, so think about it. We will come there. So it's a k stage pipeline. It takes latency is k cycles because every instruction coming in, you cannot see it outside. Suppose if you see the timestamp T1 and then you look at the timestamp Tn, then this instruction from T1 to Tn will be k cycles. It will be either minimum, it has to be k cycles, or it could be more if some stage is taken more time. Otherwise, it cannot be faster than that. So throughput is what? It is 1, ideal condition. Let us compute the speed up now. Okay, this you understand. 1 instruction is coming out every cycle in ideal say, and then I'm saying ideal condition. Here also k cycles is ideal condition because in a normal condition it will not be k cycle. It will be little more than k cycle. Okay, it will take more time. Some instruction may take more time. So we'll talk about it later. Similarly, throughput is ideal is 1, but it will be less. Please remember, don't say throughput will be in a normal condition, it will be more. No, here it will be less, whereas it will be more here. So you should know which will be more and which will be less. It's very obvious. Ideal condition is it cannot escape this k stages in the pipeline, so it will be k cycles. But if the situation is not very good, some stages take more time, then it will take more cycles than k. So k will be, the latency will be more in a normal situation. Similarly, ideal condition throughput is 1 instruction coming out. But in a normal situation wherein some instructions get blocked for some reason, it will not be 1 instruction, it will be much less than that. So maybe 0.9 instruction or 0.8 or whatever, but it cannot be more. So ideal situation and the normal situation will be different. Now, what is a speed up? How do you define speed up? Pipeline structure and a non-pipeline structure, how do you compare them? It is based on the cycles taken for n instruction. Okay, we take n instruction and then see how much of cycles it would have taken in a non-pipeline processor compared to a pipeline processor. In terms of cycles, I take some n instructions, I pass it through a non-pipeline processor, and if I assume that it is each of them are taking k cycles, we saw that it is nk, right? We saw. In this case, we saw that it is k plus n minus 1. Which is smaller is very obvious. This is smaller and this is bigger. So you will have a speed up which is more than 1. That's some good amount. Okay. And it has got some relationship with the k also. So let us now look at the derivation. You know that it is nk. This is k plus n minus 1. So do a simple mathematical jugglery and divide both denominator and numerator by k, n divided by n, then you get only k here in the top. You are dividing it by n here. And if you divide this by n, what will you get? You will get a k by n term. It is there. And n by n term will become 1. And minus 1 by n you will get. Okay. You will get this term. Now I want to simplify this equation. Assume that always we are going to not see pass some 2 instruction and then see what is the speed up. If you want to compute speed up, you have to pass some thousands or millions of instructions and then see how the pipeline is behaving. Okay, you cannot pass some 10 instruction and then find out the speed up. So n will be much higher than k. So I can conveniently remove this. I can also conveniently remove this term. Then what I get is k. So ideal situation, if n is infinite, the ideal speedup would have been k. So this is the derivation. But you might be now thinking, I showed you some 5-stage pipeline and a deep pipeline. I said this is having 5 stages and this is having 9 stages. Okay. Then you may think that this guy is better than this CPU because ideal speedup is k. So you will get a speedup of 9 if you have a deep pipeline, whereas if you have only 5 stages, you will have only 5. Maximum speedup cannot be more than 5. Do not assume. I'm saying do not assume. I will tell you the reason. Keep it in mind. Then later on we will study in more detail and you will be convinced. You cannot keep increasing the stages and expect a speedup to happen because of so many reasons. One simple reason I will tell you. We will study them in detail later. If you see the program, normally whatever we write, okay, let me just I take some time to explain this, and then we'll break. If you take so many instructions, don't think that all the instructions will be sequentially in nature. There are some jump instruction, jump on carry. There are some call. There are some return, and then branch. There are so many instructions like this. So if you get all add, multiplies, move, and only those set of instructions which do not change the flow of execution, then the pipeline is great to have. More stages are better. But if your code is having so many branches, that means what? It is executing some sequence of instruction and then going and executing some other sequence. Now, imagine a situation wherein you are taking a decision here that it has to go to some other sequence. Now, so many other instructions following this, they are all in the pipeline now. Because before this branch was taken, the PC was incremented sequentially and it has fetched other instructions in the sequence and they are all in the pipeline now. But we are saying now, branch, I cannot now execute this instruction. I need to go to some other place and execute a new set of instruction. What happens? I need to flush the pipeline. I have to forego whatever has happened here. I should just forget it and then start with a new fresh pipeline starting from this address, because I am fetching these instructions here which are no longer valid, because I am supposed to go take a branch and execute an instruction here. So what is the impact of having a 5-stage and 9-stage? In a 5-stage, you have to forego maximum 4 instructions that you have fetched. Whereas in the 9-stage, you may have to forego in the sense you have to forget about 8 instructions which have been partially completed. You have to forget all of them and then start fresh again. So you will waste more time in terms of flushing the pipeline and then starting again fresh. So having more pipeline is not a solution. More stages is not a solution. Okay, I'm just giving you a heads up. Try to think about it. We will talk about it later. So, but ideal speedup says that it is a k cycles. Okay, a number k, it is not, it's a unitless number because you are comparing cycles by cycles. So it's a unitless quantity k, which is equivalent to the number of stages in the pipeline. Okay. So we will take this quiz before we take a break. Okay. I'm not sure whether I am going to poll now. So please take a piece of paper and write down the answers. Are you guys ready? Somebody can share the answer also on the chat if you are ready. Just write five values, one after the other. No one is giving answer. All of you are taken a break already or what? Guys, I will give break for sure. No response. Okay, good. Very good. So I want 4 answers. Someone is giving only 3. Okay, good. So let me not wait. I think you are all maybe taking time to write down. So number of stages in the pipeline, very obvious. And latency, I said that everybody has to go through 5 cycles for sure. So ideal condition, maybe I should have written ideal. Okay, please, maybe I should change that also. 5 cycles, ideal situation. Throughput is 1 instruction per cycle, and ideal speed up is 5. Okay, 5 times. Very good. And a little modification here. Suppose if I say that mem stage in the pipeline, it's also 5-stage pipeline, but mem stage take 2 cycles. Okay, mem stage take 2 cycles. Now, which are the numbers will have different values? Why 10? Somebody is writing 10 or 1 and okay. So let me tell you, number of stages in the pipeline is still remain the same, 5 stages. Let me see whether I made any mistake. Latency is how much? Can you guys tell me? Somebody, you can say, tell me on audio also. What will be the latency? Yes. Latency is what? You should remember the definition. It is the number of cycles a particular instruction would have to spend inside the pipeline. Because one of the stages having 2 cycles, even though there are 5 stages, it will take one more cycle extra. So latency will be 6 cycles. It will take 6 cycles. Every instruction latency will be 6. Now, what is the throughput? Number of instructions coming out of every cycle. It will still remain to be 1 because only the latency is more, but after that it will all come out. One instruction will come out every instruction. Okay. So ideal speed up will be 6 times compared to non-pipeline CPU. I hope this is correct. Okay, fine. Now one more before we go, guys. I will start polling now. If you want to quiz 5.1, quickly give me the answer. Actually, most of you are getting it wrong. Let me explain here. In a 5-stage pipeline CPU, the number of instructions at various stages of execution inside its pipeline will be 5 at the end of the first cycle on reset. On reset, what happens? Everything is erased. Pipeline, not only pipeline, every register is reset, and the CPU is going to fetch the instruction first from a known location on reset. So that means pipeline will be empty, should be made empty. And then I'm saying at the end of the first cycle. So what happens? One instruction would have come in, it would have been fetched, but remaining stages will be empty. So this statement saying that there will be 5 instructions in the pipeline is false. So there are 10 people who have answered so far as false. Very good. But those who made a mistake, they forgot what is reset, which I taught in computer organization everywhere. I don't know. Okay. So no problem. Next question. Let me relaunch it before the break. It is very obvious. Maybe whatever mistake you made earlier, don't do it now again. Okay. I hope all of you are getting it. I will not wait for the answer, but you are answering it. So let me not. Good, good. Okay. So share the result. Very good. I don't think I need to explain this. Okay. So guys, you want a song or not? I'll keep it quiet otherwise.
Oh,
Quiet?
song.
Song. Okay, fine. I'll play some songs. So meet after 10 minutes. What is the time now?
Is 2:20.
So 2 for 30, right?
Yes.
Okay, guys. Bye-bye. Welcome back. Now let me explain. See, I just now spoke about, one second, I am hearing a echo. Okay. I spoke about having multiple stages in a pipeline, and then I told you that there are some control instructions which may take the execution to different address, and if you have to change the flow of execution, we need to refresh that pipeline. That means we have to flush out all the instructions which have already entered the pipeline and then restart again. That is one issue with the program structure, because if you recall, any software that we write normally will have around 30 to 40% of control instructions. Rest of it will be a sequential data processing instruction, but there will be some control instruction which are like jump, branch, and call, function call, and in a higher level language, it's like if or a switch statement or for loop. There are function calls. They're all control flow statements wherein the flow of instruction get changed. So pipeline is good only when you have a sequential instructions arranged in the memory, and they need to be executed without changing the order. If you have to change the order of execution, the pipeline has to be again refreshed and the new instructions should be brought in. So whatever job has been done by thinking that those instructions in the future will be executed, we would have realized that we have to jump to another address and we have to discard all that. So that is an one issue. Now, another one important thing with the RISC processor and a RISC processor suiting a pipeline structure. Okay, I will tell you why RISC processors are very easy and very convenient to design a pipeline for it. Okay, if you want to construct or design a pipeline for a RISC processor, it is much easier than doing it for a CISC. That is my discussion now in this slide. And I will refresh on what is RISC and CISC, reduced instruction set computing and complex instruction set computing, which is CISC. The features of RISC are, it has got fixed instruction width. If it is a 4-byte or 8-byte, it will be always, most of the instructions will be of fixed length. And then register set is, maximum number of register sets are there, but the structure of the instruction is uniform. That is source register and then destination registers. They all occupy a particular location in the instruction. So it is easy to decode. And another major important characteristics of RISC is load and store. Load and store are different instructions, and the rest of the all arithmetic and logic instructions are different. So these other arithmetic instructions always take operands from register set. They take the operands from registers. They do not take from memory. Memory instructions are only these two, load and store, and then the families of load, store, and then push and pop, which is also a memory instruction because it is pushing some data into the stack or popping it from stack. That is also memory operation. And rest of the arithmetic operations are all, logic operations are all register based. That means their parameters, operands are all coming only from registers. Now, what is the advantage of having operands? That is, suppose if you are adding, add R1, R2, R3, what is the advantage of having operands from the register? Because you can fetch them from the register which is locally available. So most of the instructions which are suppose arithmetic operations, if all of them are using registers only as an operand, then they all can be accessed from the register set within a one single clock cycle. You can even access 2 or 3 operands without any issues. So fixed time it will take. Whereas memory always involves more amount of clock cycles. So pipeline will be beneficial only when all the stages of the pipeline are all going without any delay. They all get completed fast within a single cycle. That is possible only when majority of the instructions are using registers as an operand rather than memory. So RISC processors are like that. They have more number of instructions which only operate on registers. So executing those instructions in a pipeline, through a pipeline, is easier and efficient. And because we have sequence of so many instructions which are there, which can be executed without any delay, too much of delay, in a RISC processor, implementing a pipeline for RISC is easier and efficient. You will get maximum benefit out of it. The speed up that we talk about, K, will not be too less than K. It will be around K. It will be little less than K, but it won't be too much lower. Whereas in a CISC processor, what happens is the instruction bits are different. Decoding takes more time. So based on the instruction that is coming in, the decoding will take different time. So you cannot say that within a one cycle a decoding will happen. So some instructions, if it is taking more time, then what happens is the whole pipeline gets delayed. Let me give an example. All of you might have seen a movie, some comedy scene of Mr. Bean. Mr. Bean
no, he will be coming down the stairs. He will be in a hurry, but there will be two old couple will be going slowly coming down. Okay, this guy wants to avoid them. He cannot do. Then he will jump here and come here and then come to the next steps. Then again you will see that old people are going here, so you'll get blocked. So it is like this. Instructions which are taking more time for decoding, if it is in the pipeline, it will delay all the instructions which are behind them. As I told you, instructions cannot just overtake any instruction in the pipeline and go forward. They have to follow the sequence. So like Mr. Bain, those instructions will be blocked until this slow instructions get out of the pipeline. So RISC is having an advantage in that sense. Okay, so most of the operands are in registers. All of the operands are in registers. So the only operations that affect the memory are loads and stores. So only few instruction formats. So as I told you, the instruction formats are fixed. So decoding will be easier, fixed decoding, because the instructions are encoded in a fixed format. So decoding is easier. Okay, encoding is correct only. That word is right. Okay, so all instructions are of same size. So hardware is simpler to implement. Pipeline is simpler to implement. So although pipelining could conceivably be implemented for any architecture, it is inefficient for CISC. It's not that I'm not saying that it cannot be implemented, but it is inefficient. So due to complex nature of CISC instructions, time taken for decoding and execution of instruction will be widely varying. Okay, one slow instruction coming into the pipeline will delay everything. Okay, so since all the pipeline stages have to be lockstep, what I mean by lockstep means they have to go in order. One instruction moves from one stage to the other stage, then next instruction will come in that place. So they have to be moving in the order in a lockstep way. Every cycle the transition has to happen. If during some cycle, as I explained in the previous quiz, one instruction is taking 2 cycles, then every instruction will have to take 2 cycles. That memory operation, if one stage is taking more number of cycles, it will delay the whole instruction in this pipeline. So there is a proverb, you might have heard it, a chain is only as strong as its weakest link. Okay, suppose you have a chain, only this particular link is weak, the whole chain is weak actually. If you pull from one to end, because one chain is weak, one link is weak, the whole chain is gone. So what do I explain here? So suppose I have a pipeline, different stages are there. One stage is taking more time. Suppose it is like a 1 weak link. One stage is taking more time. It is going to impact the whole pipeline. Those who have gone ahead will not be affected, but those instructions which are coming behind will be impacted. So that's the problem. So Intel Pentium, I showed the picture of that sometime. No, I will be showing it future. Actually, all Intel processors are CISC family processors. If you see the instructions that they give you, assembly instruction, they're all CISC type, but they implement internally RISC architecture. Okay, internally the hardware converts the CISC instruction to RISC-like instructions. It is not publicly available to the people, but it is all done internally by the hardware. So CISC is converted into RISC and then fed into a pipeline. So they have a 9-stage pipeline, 20-stage pipeline. So Intel processors overcome the problem of CISC instructions by internally convert them into RISC type. That means what? They will break up a bigger instruction into smaller RISC instructions and run it on a pipeline so that it will run faster. So just keep it in mind. Somewhere in some interview you can say that you know this and you know the reason for why it is done, because they are not changing the CISC instruction because they have to give a backward compatibility. Previous x86 instructions, the 1980s, they came up with CISC instructions. Afterwards only RISC came in. So from the beginning, it was a CISC family processor. x86 is a CISC family. So they want to have a backward compatibility. So they want to retain the CISC instructions, but they know that pipeline will have issues if they run the CISC into the pipeline. So they convert it into RISC instructions. More number of instructions will be there, but it will run through the pipeline so that they get the maximum performance. So that is the reason why Intel does like this. Whereas ARM architecture is purely RISC. It is designed from the day one as a RISC processor. So they have decided that load and store will be separate instruction, and all other arithmetic operation and logical operations will only use registers as operand. And they also fixed the type instruction bit as 32-bit and fixed coding, encoding they have done. So it was designed from the beginning as RISC processor, whereas Intel was not like that. Intel was thinking complicating the instruction was good way of implementing the processor, and later on all the university researchers came up with the conclusion that RISC is the way to do. Though it takes more number of instructions to perform a job, it is efficient in the hardware. So because of that, the whole processor families, they went into RISC way. They followed RISC way of designing processors, whereas Intel got stuck with their CISC architecture and they have to continue with that. Okay, that is the reason why Intel sometimes doesn't do well in the embedded applications, where ARM is doing very well, because you know that all our mobile phones have ARM processor in it only because of this decision they took in the first chip itself, whereas Intel went into a wrong direction when they designed it initially, and they have to stick to that because that x86 family processors have to be supported. Okay, but they have made lots of other improvements in terms of improving the performance in terms of coming up with this cache behavior and pipeline, and they are still in the race and they are doing good in the market. So I am not saying that Intel is behind ARM, but in the embedded world, ARM is better because of their power efficient processors and pure RISC family processors. So there are some pluses and minuses, whereas in servers and high-end laptops, you still see RISC, Intel based processors, and AMD also is a Intel family. Okay, they follow the Intel architecture and they design their own chip, but it is following the x86 architecture. Okay. Okay, now I am showing you the same pipeline structure now. In the rest of the class, I am not going to spend too much time. Just I will explain you this particular structure so that you understand how a 5-stage pipeline, a RISC family pipeline, 5-stage pipeline is implemented. So let me go very slowly. If you understand one picture, it is very good. This is the first cycle. Let me see instruction I. Instruction I is coming in. Assume that the pipeline is empty. So it is getting fetched from the memory. IM is instruction memory. It is instruction fetch stage. That means the first instruction has been read. It is getting read from the memory. When I say memory, it may not be from the memory. It could be from the instruction cache. I told you again, many times. Now, after that is a decode, instruction decode stage. Now, next cycle, what happens? I comes here. I plus 1 is getting fetched. Okay. See this. This is the same module which was fetching I is now fetching I plus 1 now. Okay. Don't think that there are so many instruction, these modules. The modules are not replicated in the hardware. The modules are only 5 modules in the chip. Remember, it is shown multiple times. It doesn't mean that this many blocks are there in the hardware. Only one instruction module, decode instruction fetch module, one ID, one ALU, one data memory access, and one register set. Okay, so don't get confused with the picture. Now, what is this? This is the register set. Okay, register set means in all the registers in the processor, R1, R2 to R13, whatever you have seen, it includes the flags, everything, all registers, including PC, everything is there. Now, instruction has come in. even IR is inside somewhere shown. Okay, you don't worry about that. Now what is happening in this stage? Decoding. Decoding an instruction means trying to understand what is the instruction is all about, whether it is an add operation, whether it is a mul operation, or is it a load or store. It is seen or known only here. In this stage, it doesn't know. Processor does not know what instruction has come in. It knows that one instruction has come in, but it doesn't know what type of instruction it is. Unless decoding is done, it will not know. Now, based on the instruction, remember, whatever operations are happening down the line is all based on the instruction that has come in. It is very much tied to the instruction which has been read. So we have to think a pipeline's behavior, thinking that I am getting an add instruction, thinking that I am getting a move instruction, what will happen? So based on the type of instruction coming in, they go through different things, they do different things, and they come out. Okay. So you may see here, there is a line coming here directly to ALU. There is one from ALU and there is one from here also. And here also there is data memory is skipped and then it is connected. So remember one thing, it's a hardware. So this particular input, if you are looking at the input here, either input can come from ALU or directly from here, it may come. It is not that it is giving both input together. Okay. Picture is showing like that. It's like an electrical connection, but do not assume both input will be given to it at the same time. Based on the instruction which has come, based on the decoding done here, the path will be set up. It will be, that information is passed. Okay, what type of instruction is read is passed to all the stages, and the path is set. Path is set means that signals will be, control signals will be put, and only either this path will be there or this path will be there. And ALU may perform only add operation, or it may do subtract operation, or it may do a logic operation, and or. So it depends on the instruction. Based on the instruction, the ALU can perform any different job. If you have seen the simple design of CPU, we showed that there are some control code for ALU. So those things are there already. It's not shown. It is at a higher level. These things you are supposed to understand it from the picture. Okay. Now, one more important thing in the decode stage. It is not only doing the decoding here. It is doing one more job. What is that one more job? If you see this, it is a register set, I said. So in this pipeline, during the decode stage, remember, it is very important. During the decode stage, two things are done. One is the decode job, decoding of instruction, and based on the decoding, access the operands. Suppose if I had received an instruction add R1, R2, R3. That means what? I need to add R2 and R3 and put the result in R1. Which are my operands? R2 and R3 are my operands. Then accessing that R2 and R3 is done here. Fetching the operands is also done along with the instruction decoding. Now, where does the operand come after reading? After reading from the register set, they are given to the processor, sorry, ALU. So R2 will be here, R3 will be here. It again depends on the implementation. I am assuming this is the first line, and mostly it will be like that. So R2 and R3 will be here. Okay. So the decoding job is done and the operands are also fetched and it is available at the ALU. But add operation is not done during this cycle. For I, during CC2, what has happened? It has understood that it is an add instruction and it knows that R2 and R3 are the two operands. It has also accessed the operand and made it available to ALU. But actual adding of these two should be done by ALU, and it is going to be done in clock 3. It's not doing clock 2. Hope this is clear. Now let me erase maybe partially. Okay. Now what has happened? We have R2 and R3 here, and now based on the decoding done, it has to set up the ALU that it is an add operation. That is, control signal will be sent. Okay, don't worry about it. Execution of this instruction is taken care because it knows which instruction is flowing through the pipeline now. So it is aware of, at every stage it is aware that is being passed. Okay, so it is like this. Suppose if you are checking in a flight, they are checking your ticket at the boarding time, and then you are a first class passenger. Then they give you a boarding pass with a first class passenger, and then you come to the security gate. You will be given a maybe a higher preference. You come to the boarding gate, you will be given higher preference because you are a first class passenger. When you come into the flight, you will be asked to sit in a particular seat, which is reserved for first class passenger. And when you flying, you will be given all kinds of drinks and you will be taken care of during the flight. And you exit, maybe your luggage also will come first during the when you are landing in the aircraft, from the aircraft, and landing, reaching the destination. So right through this journey, you being a first class passenger is known. Because of that, you have been given a different treatment, whereas another passenger with the economy class also going through the same thing, but they won't get the same behavior, they won't get the same treatment, they will get a different treatment based on how much they paid. So that information is available in each stage, and which instruction is going, it knows, and it will take the job, it will do the operation required for that instruction. So remember this, how it is all implemented in a hardware. You can think of this as most complex thing to do everything in hardware. See, no software is running, but when I say hardware, it's a micro program. Micro program is also a sequence of control signals feeding to each of the hardware at every cycle. So based on the type of instruction which came in, these blocks will behave differently, whereas the next instruction which is following it will get a different treatment because it is a different instruction. Though the same ALU block is working on the instruction, if it is a subtract instruction, when it lands in the ALU stage, ALU will perform a subtract operation, whereas in the previous cycle, if it was an add instruction, it will perform add operation. So every cycle, the behavior of this ALU or any other stage depends on what is coming into what is going through the instruction pipeline. So you have to keep this in mind to have a clarity of what exactly is happening. Okay, now take the example of add. I remove it. Add R1 comma R2 comma R3. It gets added here, you get the result here. Now memory operation is, if you have to access the memory, it will be done here. Suppose load or store instruction is coming, it will be taken care of here. But what you are seeing is an add instruction. It doesn't have a data memory access, so it will go through this path and come here. But it has to spend one clock cycle here, but it will be just waiting. It doesn't access the memory, it doesn't initiate any memory cycle. When the add instruction is passing through, it will just wait, it will pass on the same value out. Okay, so I will explain it with more detail. I'm just explaining it so that here you understand it. Now what is write back? The add value or add R1 comma R2 comma R3. So the result has to be written into R1. That writing into R1 is happening here. So it was computed here, addition was done, result was available, but still not written because the pipeline does not allow you to access the register in this cycle. So that value is preserved and then given here. When this instruction add reaches this stage in cycle CC5, write back happens. Into which register? R1 because it knows it is done decoding here. That information is passed. So add R1 comma R2. When it comes here, R1 will be written into. Whereas some other add instruction coming here, it results will be written into some other register based on the instruction. So that is how the whole thing works. If you understand whatever I have explained now, you are ready for pipelining. So I will show you some examples. And now what is the time? Okay, guys, I am going to stop here. I don't want to take more than the scheduled time. Let me stop the recording.